let's start with the Concise textbook first. We'll take the markings right now, and then I will continue explaining from the Dalal textbook, which is more precise and easier to understand. Note that the concepts are the same in both the textbooks. We start with the introduction. There's a definition here. Section 7.2 is entirely marked as read, which means that it is not in the scope of syllabus, so it should not come in any ICSE test. But if your school insists that you should study this, then you better do. This is some basic point which you have studied in previous standards. This is based on the kinetic molecular theory, which explains that gases are made up of molecules. They don't have a fixed volume or a fixed shape. They occupy all the space available to them. They exert pressure in all directions because the molecules move in a zigzag direction, colliding with the walls of the container. They are highly compressible because they have large intermolecular space between them, and that's because their intermolecular force of attraction is quite weak. They are highly expansible as well. If you heat them, they expand rapidly. On the other hand, if the pressure decreases, then too the volume will increase. So they are very sensitive to changes in pressure and temperature. They have low density, again because the intermolecular space is large compared to solids and liquids. They diffuse very rapidly. So we can't have two gases which are immiscible with each other. They will always mix together. And this is the definition of diffusion. They can be liquefied easily either by cooling them at a very low temperature or by applying pressure on them. So when you apply pressure on them, you are bringing the molecules together, closer to each other, and they liquefy. This is the definition of temperature. The SI unit is Kelvin, which is the absolute scale of temperature. The lowest possible temperature in the universe is 0 Kelvin. In fact, even that is not achievable, because at that temperature, matter will cease to exist. So the absolute zero definition is this. If you're using Dalal textbook, then you may learn the definition in that book. Both definitions are equivalent in both the books, but your teacher may insist that you write the definition in your textbook. Now we have a give reason, which says that as temperature increases, the pressure increases, assuming that the volume is constant. Because more the temperature, more the kinetic energy of the molecules, and more number of collisions with the walls of the container, and more pressure. Now the gas laws. This is the definition of gas laws. This is a give reason. Why should we study a gas in terms of three variables: pressure, volume, and temperature? Because they can affect each other. A slight change in pressure can affect the volume and temperature, and so on. Definition of volume. Definition of pressure. Note the units and the conversions. It will be useful in numericals. Atmospheric pressure. This paragraph is just read. Pascal's definition. This is a repetition from physics. Again, the conversions. Temperature definition, the easiest. Degree of hotness of that gas. Experiment cancelled. These two paragraphs cancelled. The conclusion simply says that as pressure increases, the volume decreases, and vice versa. That leads to the Boyle's law. Cancel this paragraph. The Boyle's law. There are two statements, 1 and 2. I would recommend the first one. Derivation is not there, but the equation has to be learned for numericals. The graph is very simple. If it's V versus 1 upon P, it's a straight line with an acute angle. But if it's V and P, then it's a curved line, a hyperbolic curve. 7.4, mark it as read, which means I will not ask in the test, and very unlikely that it will come in school test, but I can't cancel it. Cancellations you take from school teacher. Explanation of Boyle's law I have explained a little later in the video with the Dalal textbook. Significance, importance, mark this as a GR, and even this is a GR. There are some solved examples. Cancel the third solved example. This will be for practice homework once numericals are done. There is a separate video for numericals. In these numericals, again, the second one is cancelled. Even if you're using Dalal textbook, you may want to solve these numericals for extra practice. Concise numericals are slightly more challenging than Dalal numericals. Temperature volume relationship, so that's Charles' law. Mark this as a GR. This is entirely cancelled, this derivation. And even Charles' law statement will refer to the second statement, which is easier. This original statement is quite technical, but if your teacher insists that you learn it, then you better do. I will accept both the laws in the exams. This is the equation we'll use for numericals. The explanation of all this is in detail coming shortly when I start with the Dalal textbook. Graphical representation of Charles' law. Cancel this graph, and even this graph is quite complicated. There is an easier version in Dalal textbook which will be visible shortly. Here they've used degree Celsius on the x-axis, but if you use Kelvin, we can draw a graph from the origin. Explanation. That will be done a little later. Significance, mark it as a give reason. Absolute zero, cancel all this. This is a repetition, by the way. Again, mark this as a definition. Conversion of degree Celsius to Kelvin, that's straightforward. And again, more solved examples. Here, cancel the eighth sum. Mark this definition of gas equation. Give reason here, very important give reason. Why do we have STP? More about it later. Definition of STP, these are the values you'll learn. Another give reason here. And then more solved examples. Section 7.12 is entirely cancelled. Entirely, even the solved example 13 and 14 are cancelled. And then we start with the exercise, which is for homework. The introduction is not in our syllabus, but we need to be aware of the properties of gases and the explanation of these properties with the help of kinetic theory. Gases are very different from solids and liquids because they don't have a fixed volume, neither do they have a fixed shape. That's because the intermolecular space is the greatest in gases and the intermolecular forces of attraction is the least in gases. Hence, they are also highly compressible and they diffuse very quickly. Now, how do we define gas laws? There are certain rules which a gas follows when subjected to a change in temperature, pressure, and volume. These three physical quantities are important when we are talking about gases because gases are very sensitive to the slightest change in temperature, pressure, and volume, unlike liquids and solids. So these laws can't be applied for liquids and solids. They can be applied only for gases. Temperature is the indicator of the average kinetic energy possessed by a molecule. The SI unit is Kelvin, although we use degree Celsius and in some places even degree Fahrenheit. So as you heat something, the kinetic energy of the molecules increases and the temperature increases. Pressure, that's force upon area, that's the formula. In case of gases, the pressure is exerted on the walls of the container in all directions. And that depends on the number of collisions that the molecules make with the walls of the container per unit area. Volume is the total space occupied by the gas. And gases will fill up the entire space available to them. Pressure's SI unit is pascals, although we do measure it even in centimeter of mercury, millimeter of mercury, and atmospheres. Normal atmospheric pressure is 1 atmos, which is 76 centimeter of mercury. Volume, SI unit is meter cube. Other units are liter. You should know all the conversions. 1 liter is 1000 centimeter cube, which is also 1 decimeter cube. Also, 1 centimeter cube is equal to 1 ml. Now let's understand the relationship between pressure and volume of a gas. Here, we'll assume that the temperature is constant. If we do an experiment, we would notice that as the pressure changes, the volume changes as well, and they are inversely proportional. From this graph, you can notice that as the pressure is increasing, the volume is decreasing, which makes sense, assuming that the temperature is constant. If you apply a greater pressure on a gas, it will occupy lesser space. Now let's understand the relationship between temperature and volume. Again, there is a graph to understand it better. This time, they are directly proportional. But that works only if we are keeping the pressure constant. As the temperature is increasing, and by the way, it's in Kelvin, the volume is also increasing, which again makes sense. As the temperature is increasing, then the kinetic energy of the molecules will also increase and they will expand. All objects expand on heating. So hence the volume increases, considering that the pressure is kept constant. Remember, conversion of degree Celsius to Kelvin is done by this formula. The degree Celsius temperature plus 273 will give you the Kelvin temperature. That means if your temperature, room temperature, is freezing cold, 0 degrees Celsius, then in SI units it is 273 Kelvin. While solving numericals, we have to use the Kelvin temperature. We cannot use degree Celsius values, otherwise the answers will be wrong. So now we start with the laws. The first law is Boyle's law, which states that if the temperature is constant, then the volume of a given mass of a dry gas is inversely proportional to its pressure. So this is straightforward. Volume is inversely proportional to the pressure. Of course, if pressure increases, volume decreases, and vice versa. But there are three assumptions we are making here. Number one, the temperature is constant. Second, the mass is constant. And third, it's a dry gas. There is no moisture involved here. So when you state the Boyle's law, you have to learn it word to word. If you miss any of these keywords, you won't get marks. A mathematical way of writing Boyle's law is that pressure into volume is a constant. Or you can say P1 V1 is equal to P2 V2 is equal to constant. When we will do numericals, you will see how this works. Look at this solved example. They have mentioned that the temperature is constant. That was very important to use Boyle's law. We have to mention the law being used. The initial volume was given, the final volume is given. You can read the whole question here. And the final pressure is given, and they've asked us to find the initial pressure. Note that the units should be same here and here. We need not convert it to SI units. Just substitute the values, cross multiply, and get the final answer. So the numericals are very easy in this chapter if your formulae are well studied. Next we go for Charles' law. First of all, we need to understand something called absolute zero. That is the lowest possible temperature on the Kelvin scale, the SI unit. The lowest possible temperature in the universe is minus 273 degrees Celsius. That's right. Nowhere in the entire universe can we find temperatures less than minus 273 degrees Celsius. And that is the starting point of the Kelvin scale. We call it 0 Kelvin. That's right. 0 Kelvin. No degrees here. No 0 degrees. Just 0 Kelvin. Negative temperature is not possible in Kelvin scale because this is the lowest possible temperature. And if you look at the graph, you will see that as the temperature is increasing, the volume is also increasing because, gases expand on being heated. So now we know what is absolute zero and the absolute scale called the Kelvin scale of temperature. Fortunately, when the temperature increases by 1 degree Celsius, it also means that the temperature has increased by 1 Kelvin. So the magnitude of 1 degree Celsius and 1 Kelvin is the same. And we know how to convert them. The 0 degree Celsius is 273 Kelvin. If I say that the temperature is 25 degrees Celsius, that would be 298 Kelvin. So now tell me, what is the boiling point of water at 100 degrees Celsius in terms of Kelvin? What is the boiling point of water in Kelvin? That's right, it's 373 Kelvin. So, Charles' law. Well, volume is directly proportional to temperature. But three things are constant. Pressure remaining constant, the volume of a given mass of a dry gas is directly proportional to its absolute temperature. Keywords. Pressure constant. Given mass, that is mass is constant. That doesn't change. Dry gas, no moisture allowed. Absolute temperature, don't just write temperature, because this formula, which is V1 upon T1 is equal to V2 upon T2 is equal to a constant, will work only if the temperature is measured in terms of Kelvin. And this is the mathematical form of Charles' law. And again, the numericals will be straightforward. Look at this question, read the question. They've given the initial volume and the initial temperature. They've given the final volume and they've asked the final temperature. Pressure is constant is mentioned, so we can safely use Charles' law. This is the formula, substitute, cross multiply, and get the answer. Now, they had given the temperature in degrees Celsius. Note how we convert it into Kelvin first. And we get the answer in Kelvin. We will back again subtract 273 to get the answer in degrees Celsius because they had asked the question in degrees Celsius. So that's a silly mistake which must be avoided. Don't use degrees Celsius values in the formula. We'll be doing a lot of numericals of this type in the next video. So we have the Boyle's law linking pressure and volume. And we have the Charles' law linking temperature and volume. In both the cases, one thing was constant, either the temperature or the pressure. But in reality, practically, it's difficult to keep any one parameter constant. When one thing changes, the other two also change. So let's combine both the equations to create a gas equation for all three terms, pressure, temperature, and volume. So the gas equation is an equation used in chemical calculations for calculating the change in volumes of gases when pressure and temperature both undergo a change, thereby giving a simultaneous effect of changes in temperature and pressure on the volume of a given mass of a dry gas. Now you try it. That's a definition you can learn for 1 mark. So we had the gas laws. Let's combine them. So this is the master equation of gas equation. P into V upon temperature is always a constant. If you notice, if T is constant, then this becomes the Boyle's law. And if pressure is constant, V upon T, that becomes the Charles' law. So combination is P into V upon temperature is equal to always a constant for a given mass of the same gas, dry gas. So again, the numericals based on this are very straightforward. Look at this sum, for example. Read the question. At STP, when they say STP, it means standard temperature and pressure. More about it soon. But pressure, what's the standard temperature? it's taken as 0 degrees Celsius. Whenever they say standard temperature, it means 0 degrees Celsius. That is 273 Kelvin, of course. What is the standard pressure at sea level? Normally, what is the pressure? 1 atm. That's right, 1 atm. Or we can say 760 millimeter of mercury. We could have used 1 atm value also here. That's fine. Volume has been given 700 ml. So the final conditions, the pressure has been given 400 millimeter of mercury. Okay, that's why we had to use millimeter of mercury here as well. If they would have given this pressure in terms of atmospheres, we could have used atmospheres even for pressure 1. New volume is unknown, so let's assume it's X, and new temperature is given, but please convert it into Kelvin. Substitute these values. Out of the 6 variables, 5 variables are known, 1 variable is unknown. Cross multiply, get the answer. So easy. But yeah, the calculations are quite challenging, which you will need to do, and don't just copy. So more numericals next time. But let's do the final theory part. Let's understand these Boyle's law and Charles' law in terms of kinetic theory. What's happening here? Let's first understand Boyle's law, which says that volume is inversely proportional to pressure. So imagine that there is a vessel or a container with a particular volume. The molecules of the gases are moving randomly inside, colliding with each other and with the walls of the container, and the collisions with the walls of the container is the reason why a pressure is exerted. And the pressure depends on the frequency of the collisions. Now, what if this wall is movable? What if we can move it and expand the volume of this container? Make sure this is airtight so that no air from outside can enter in or the gas cannot leak out. So it's like a piston which we have moved outward, increasing the volume. Now, the mass of the gas is the same. The number of molecules of the gas remains the same. So now, do you think that the number of collisions per second per unit area, or the frequency of collisions with the walls, will increase, decrease, or stay the same? Well, clearly now each molecule has to travel a greater distance to collide with the walls. So the frequency will decrease because the kinetic energy hasn't been increased here. The temperature is constant. Remember that. Temperature is constant. So when the volume was increased, what happened to the pressure? It decreased. So this is how we can explain Boyle's law with the help of the kinetic theory of gases. Same is true if you decrease the volume. If you just halve the volume, so now the same molecules have such short distances to travel before colliding with each other and the walls of the container. So the number of collisions per second per unit area will increase, the frequency of collisions will increase, and the pressure will increase. Since the volume is halved, pressure will double. That's right, if the volume is halved, the pressure is doubled, assuming that temperature is constant. So that explains Boyle's law. Now let's understand Charles' law. Now, Charles' law says that as the temperature increases, the volume will also increase, which can be seen in daily life. If you have a balloon filled with some air, and if you slowly warm that balloon and the air inside it warms slowly, you will notice that the balloon is expanding. The volume of the balloon and the air inside it is increasing because the temperature is increasing. Of course, after a certain limit, the balloon will burst. But this is clearly a case of Charles' law being applicable, assuming that the pressure is constant. But let's explain this with the help of the kinetic theory. So here, it has a fixed volume and a temperature. Now I increase the temperature. So the kinetic energy of these molecules increases. Now they travel with great vigor and they collide more often with the walls of the container. So the pressure should increase. But I just said I will keep the pressure constant. I'm heating it. The temperature is increasing. Then how can I keep the pressure constant? Obviously, I will have to increase the volume, just like I did here. So now what will happen is that the volume has increased with the increase in temperature, but the pressure is still the same because the frequency of collisions here and the frequency of collisions here will be same. How? Because after heating it, the kinetic energy or the velocity with which they were moving was more. So even though they have to cover more distance, still they will be able to collide as often as earlier when they were cold. So simply speaking, as you heat something, it expands. So they are directly proportional. If the temperature, absolute temperature, okay, Kelvin temperature doubles, the volume also doubles. Now, the standard temperature is taken as 0 degrees Celsius and the standard pressure is this. There is no standard volume, by the way. But why do we have this normal temperature pressure or standard temperature pressure? That's because, as I said, gases are very sensitive to the slightest change in temperature or pressure. The volume changes dramatically. So if you want to compare two different gases, the volumes of those two gases or any other parameter, it will be unfair to compare them when they have different temperatures and different pressures. For example, if I ask you a question that will hydrogen at 5 degrees Celsius have more volume than oxygen at 5 degrees Celsius, that's not a valid question because it also depends on the pressure acting on those two gases. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.